Okay, so we are going to start with the outer regions of the atmosphere. So this is anything above the stratosphere. Okay, so a couple layers up. And these are things that is like what chemistry is going to happen regarding sunlight. So when sun is coming down to hit the earth. Okay, so beyond the stratosphere, there's a few molecules of nitrogen and oxygen, and those are what kind of protect us from the sun's reaction. So beyond the stratosphere, a few molecules of nitrogen and oxygen. Of N2 and O2. They are kind of a defense shield for radiation. Okay, if all that radiation actually made its way to Earth, we would not be here. Okay, so it would kill life on Earth if it could reach us. Would kill life on Earth. I'm just going to put that would kill life on Earth. Okay, so if we weren't protected by these regions of the atmosphere, we would not be here. Okay, a lot of other planets don't have atmospheres like this, and that is part of the many reasons that there isn't life or hasn't been found life on those other planets. So what processes do happen in the upper atmosphere? There are two main types of chemical reactions that we are going to talk about. The first one being photodissociation, and the second one being photoionization. So we have heard the terms in this word before. Photo would mean like light, right? And dissociation would be breaking apart. Okay, and photoionization would be light used to ionize, right? Take an electron off and turn it into an ion. So those are the types of reactions that actually happen: photodissociation and photoionization. So photodissociation is technically the rupture of a bond by absorbing energy. Rupture of a bond by absorbing energy. Okay, now it always requires energy to break a bond. Photodissociation would just be using light energy or some type of electromagnetic radiation in order to do it. Okay, so the reaction looks like this. You've got oxygen, and you put in some type of energy. Now, in these types of reactions, you will see us represent energy like this, HV. Okay, because if you actually look at the equation to solve the energy, it is H times the frequency. So it's actually based on the frequency of light and how much energy we're going to need. So oxygen plus HV. So right, this is how we're going to write energy for right now. Energy breaks it into two oxygens. Okay, now we never see oxygen like this, right? Oxygen doesn't like to be a single. It is very, very reactive. But this does happen. That's what happens when it absorbs that enough energy. And I told you before, the delta H for this, or the amount of enthalpy or energy needed for reaction, is positive 495 kilojoules per mole. So what this means is in order to break up a mole of O2 molecules into single oxygens, requires 495 kilojoules to do that. And it is endothermic. Breaking things is always endothermic. Okay. Now, photoionization, on the other hand, is not breaking a bond, but that's removing an electron, turning it into an ion. So photoionization is the loss of an electron from an atom or molecule, from atom / molecule. Okay. It's very similar to ionization energy. It's similar to ionization energy. Okay, we're just using the sun's light in order to actually ionize these things. Okay, so the reaction for this one's going to look like this. I have an oxygen molecule, and it's going to absorb some amount of energy, whatever that energy may be. And instead of breaking it into two oxygens, it's actually going to take an electron off. So now it's O2 plus and one electron, also weird looking molecule, right? We've never seen anything like this. Okay, now the amount of energy required for this is actually a lot higher, right? This is very unstable, doesn't happen that often, is positive 1205 kilojoules per mole. Now, in certain regions of the atmosphere, this amount of energy is readily available. So we're going to talk about what regions photodissociation occurs and what regions photoionization occurs and which molecules actually do that. Okay. Before I get there though, we're going to do a little bit of wavelength energy frequency review, because you will need to be able to calculate the amount of energy needed to do these reactions, or how many of these reactions can happen based on the amount of energy we are getting from the sun. So wavelength and energy for photodissociation, essentially, so these are our energy equations, right? These are the two equations that we need, and these are from Chem 161. It's energy equals H V, or nu, and C equals lambda V. These are our two equations. H is a constant and C is a constant, okay? H is Planck's constant, which you will be given 6.626 times 10 to the negative 34th. Yeah, I think that's right. Yeah, negative 34th joules seconds. And C is the speed of light, which is 2.998 times 10 to the 8th meters per second. Okay, you'll be given both of those values, but this can help us to calculate energy. Okay, so E stands for energy, and the lambda stands for wavelength. We usually have it in meters or nanometers. Okay, and V, or nu, like it's a funky V, it's the letter nu, is frequency. Okay, frequency is how many waves essentially will pass a point for a certain period of time. So the unit is per second. So it's like this many per second. So it's 1/second, which is the exact same thing as a hertz. Okay, so I will talk about those in a minute. These are all related. You can combine them into an equation if you need to, but this is how we find the amount of energy associated with photodissociation and photoionization based on the wavelengths of light coming from the sun. Okay, so this is really important above 120 kilometers. Okay, so important above 120 kilometers, because that's where we're going to be interacting with the sun's light. And that's where most of the high energy radiation gets absorbed, and it is used to do chemical reactions. So important above 120 kilometers. This is where it absorbs a majority of high energy, I'm going up here, radiation. Okay, so we've got these reactions happening, and we can actually calculate the amount of energy associated with these. So below here, I have the electromagnetic spectrum, also something you don't have to have memorized. There's a couple things that I want you to notice, though, okay? And we're going to look at these equations as well while we do this, because if you look at it, okay, wavelength, as wavelength decreases, so this would be like shorter and shorter and shorter waves. So long radio waves are very, very big. Radio waves are very, very big, 10 to the second meters, okay, down to infrared. And then the visible spectrum is right in here. And then UV, X-rays, gamma rays, and cosmic rays. These are much more damaging, okay? And if you look at the equation, energy equals H times V. Well, energy is actually related to frequency. So I've got wavelengths getting shorter and shorter and shorter and shorter as frequency gets higher and higher and higher, because technically all of these waves are moving at the same speed. It's just that is the wavelength. So the length between two peaks. So I'm going to draw a couple of waves here. Okay, so this is the wavelength, okay, the distance between two peaks. As it gets shorter and shorter, they get closer and closer together, and so we have a higher frequency, so we have a lot more waves passing a point per second. So these are inversely related. As wavelength decreases, okay, frequency increases. Okay, so those are inversely proportional. And then energy goes kind of with frequency, because as the frequency increases, so if you look at where the nu or the V is, if that increases, energy is also going to increase. So energy increases as frequency increases. So cosmic rays and gamma rays are super energetic, super short, and super damaging. Okay, so we need the upper atmosphere to kind of take care of those for us. Okay, so we're going to do some calculations with these. I want to calculate the wavelength of light required for the photodissociation of molecular oxygen. So I told you before how much energy was required to dissociate a mole of oxygen, and I want to know the wavelength of light required required. Now, I am going to make one note about these two equations here. This is the amount of energy for one particle. Okay, so like if one wave hits one molecule. Okay, so these are for one particle, which could mean atom or molecule. Okay, these equations, one particle. So if I'm talking about a mole, you are going to have to divide by Avogadro's number in order to get the amount of energy for one molecule. All right, so that's going to come into play here in example number 1. Say, calculate the wavelength of light required for the photodissociation of molecular oxygen. Okay, well, I know that the delta H for this reaction, because I had told you before, is 495 kilojoules per mole. Okay, well, I can't use the energy equation or the speed of light equation unless I'm talking about one particle. So I'm going to go ahead and convert this to energy per particle. Okay, so 1 mole has 6.022 times 10 to the 23rd molecules. Okay, so that means if I do this calculation for 6.02 times 10 to the 3rd, get 0.219 per molecule. Okay, so that is the energy required to break up one molecule of oxygen. Now it's a very, very small, okay, so that's the energy. So now that I've got it to per molecule, this is the E in my equations. Okay, so now I can do, well, what am I trying to find? It says calculate the wavelength of light. Okay, now you do need to know wavelength is lambda. Okay, now lambda and E are not in the same equation, so I am going to have to use both equations. I have E. So first thing I'm going to do is E equals HV or H nu and solve for nu. And then I'm going to plug this into C equals lambda V and get my lambda. So I'm going to walk through that really quick here. Or if you've got the algebra, go ahead and skip ahead. Okay, so I'm going to plug this in. I've got 8.2199 times 10 to the negative 22nd. Actually, I'm going to go ahead and put this into joules because my H is in joule seconds. I wrote it above. So they both have to be in joules. All of our units have to match. So I'm going to multiply by 1,000, which means this is not going to be negative 22. It's going to be negative 19 joules. Okay. Equals H. H is a constant. That's 6.626 times 10 to the 34th, negative 34th joules times seconds. And then I can solve for V or nu. Okay. If I get that, I get that V. I'm going to move this label here. V is 1.24 times 10 to the 15th 1/seconds. 1/seconds is the same thing as a hertz if you were comparing this to the electromagnetic spectrum above. Okay. All right. So I have that. Now I'm going to use C equals lambda V. I'm going to solve for lambda. So C is also a constant. So I got 2.998 times 10 to the 8th meters per second equals lambda times, I'm going to plug in this frequency here. Okay, solve for lambda. And I get 2.41 times 10 to the negative 7 meters. Okay, so the wavelength of light needed to do photodissociation of oxygen is 2.41 times 10 to the negative 7th meter. So if I look up here, and I find 10 to the negative 7th-ish, right, of wavelength, that would be about here. That's in the visible spectrum. So visible light actually causes photodissociation of oxygen. Okay, so that's really important to know. Just visible light can cause photodissociation of oxygen. It has to be a specific wavelength, but if we've got visible light coming in, that's going to happen. Now, if I did this for the photodissociation of nitrogen, that will only happen with a very high energy bond. So if I did the same calculation, but instead used the number for nitrogen, so if I go ahead and did that, I would find that I need much higher energy. So it's much more unlikely to happen for photodissociation of nitrogen because the wavelength is going to have to be way shorter and way more energetic. So photodissociation of nitrogen is high bond energy So it doesn't readily undergo PD. PD. Unlike oxygen, who can very easily be dissociated into oxygen. Okay, so we are going to talk about the upper atmosphere here with regards to electrons. So this is going to be photoionization, taking out those electrons. And what we're going to focus on first is the highest level, the thermosphere or the ionosphere. They are the same thing. You might hear it referenced as either. So I do actually want to talk about why it's called the thermosphere or the ionosphere, because if you look back at our first page, if I look back at this graph, the ionosphere, the thermosphere, the temperature starts to go back up again. Okay, call it the thermosphere because of that temperature change. Now, why is that? And it's really because of all of these reactions that happen in the thermal or ionosphere, those photoionization reactions. So this was actually discovered a very, very long time ago. In 1901, they discovered by radio signal from 2,900 kilometers away that electrons have got to be abundant in the upper atmosphere because we're seeing photoionization. So things breaking down and becoming ions. So they had to like justify that this had to have been happening because they were seeing the results of photoionization. So the couple notes I want to make here is that these were discovered by radio signal. Discovered by radio signal. Okay, so you can kind of see in this little chart here, as we were getting up into the ionosphere, they're actually detecting those waves because we were seeing variations of what our radio waves were doing. They were actually like bouncing off. So they were discovered by radio signal. Electrons must be abundant up there. So electrons must be abundant. Okay, and that was because we were seeing those differences in the upper atmosphere where they thought there wasn't anything. But there's got to be electrons up there. And the reason they're there is because of the photoionization process. Electrons must be abundant, and they are because of the photoionization. So these are the important photoionization processes here: nitrogen, oxygen, and then remember those single oxygens tend to break up when they absorb energy. So there's also single oxygens that can be photoionized as well. Okay, so these guys here each produce an electron. And that's when they are absorbing the radiation that's high energy, because these are all really big numbers, right? So they actually need very high energy. So they're taking the worst of those that radiation from the sun. So these reactions here absorb radiation in the high energy region. High energy region would mean short wavelength, high frequency, and this would be of UV. So it's taking in the really bad UV rays from the sun. So similarly to what we did previously, I want you to calculate the wavelength used for photoionization of O2 instead of the PD. So use the photoionization energy here, 1205 kilojoules, that would be per mole, to calculate the wavelength, similarly to before. Go ahead and pause. So if you did this, you end up with 9.9 times 10 to the negative 8 meters, which is in the UV region if you check your electromagnetic spectrum.